Force is a very important concept in physics. In fact, the Newtonian mechanics can be considered as a study of forces. Do you agree? Perhaps you can remember Newton's 3 laws in mechanics. All of them involve the force. The first law, inertia, talking about what would happen in the absence of external force. The second law provides a quantitative relation between the force and acceleration. Based on acceleration, the motion of the object can be solved, can be predicted. The third law tells us that force always appear as a pair. So when we have the one force, you have to consider another force, which is opposite in direction, but equal in magnitude. So that 3 laws are all concerned about the force. So actually, the 3 laws of Newton's mechanics provide the foundation for dealing with different mechanical problems. Over the past 100 years, and many problems have been solved, and including today's including today, we still use Newton's Newtonian mechanics to predict how the rocket be launched and how to go from Earth to Mars. Okay. Unfortunately, the importance of this tradition or the achievement of this Newtonian mechanics had been underestimated by many YouTubers who are trying to advocate that the future for physics must be based on quantum mechanics and Einstein's relativity. Of course, this series is focused on the field and field theory, in which we'll eventually discuss various abstract ideas and approaches introduced in the quantum field theory, including the standard model or string theory. But before that, I would like to give a short introduction of Newtonian mechanics to demonstrate how force was originally treated as a key to solve the problems in physics. Welcome to Young Tuition. This is a unique channel to explore and share the basic knowledges about the issues in physics and beyond. If you like this channel, please subscribe, and also please inform other people to subscribe so that I can provide more interesting and in-depth short videos on a variety of the subjects. Okay, let's go to our blackboard. Where shall we start? Yes. So what is Newton's mechanics? The objective of Newtonian mechanics is to describe and predict the motion of the object, either the flying object near the surface or the remote object in the sky or in the heaven. So that is the ground objective for Issac Newton before his journey started. To do so, Newton have invented calculus in the first place to quantitatively describe the 3 quantities of motion, namely the position, the velocity, and the acceleration. If you know one of them, the other 2 can be calculated, can be derived by using calculus, either use differentiation or integration. This was the first time that how the motion can be so accurately described. So that is a great achievement by Issac Newton, and in which the calculus he invented played the unique role. To be specific, if we consider the motion of the object in space, we first have to choose the frame of reference in which we can set up the three coordinates, three-dimensional coordinates, x and y. These, based on in this coordinate, then we can describe the position of object. If we just focus on one-dimensional motion, we can just write the position as the x as a function of time. Of course, in the 3D scenario, we have to add another two components, y and z. But the method is the same. Once we know the position, then we can define the velocity as the first derivative of the position, denoted by this derivative or x dot. And in addition, Newton's introduced how to describe the change of velocity. So that is a very new idea in his days, that acceleration must be taken into account in order to describe the motion observed. So that is three equations. You can also consider this is a differential equation. That three quantities can be used to describe the motion of any object in space. Okay, so if you know one of them, then we can know all. So which one did Newton choose? He chose acceleration, because he first realized that the acceleration is determined by the force acting on the object, which is consistent with his first law. Actually, his first law is based on Galileo's experimental observation. And also that is also consistent with the, also for the first time, and it's called the paradigm shift, that Aristotle's pure philosophical reasoning was thrown away, abandoned. Because according to Aristotle, the moving object must be sustained or must have the force exerted on the object. So both Galileo and Newton realized that is not the case. Okay, so therefore, from point of view of physics, the simple relation between acceleration and the force was established in his second law. In other words, instead of go to observe and just purely observe the phenomena of the motion, we can actually focus on or identify how many forces acting on this object. For example, these two forces represent the gravity and the air resistance force, two forces. Once we know these two forces, then the trajectory of this projected motion can be mathematically determined. That is essence of Newton's Newtonian mechanics. A good example is using Newton's mechanics is to study the mass on spring, which provide which is eventually known as the harmonic oscillator. Okay, this is a classical one. Okay, later on, I'm going to discuss the quantum harmonic oscillator, which although the description is different, but the idea, the system, the model is the same. So in this simple system, we have the object connect with the spring, and we put this object into the liquid so that when the object is moving, they will generate the the resistance or dragging force. And in these issues, the acceleration, these on the left-hand side is the product of mass and acceleration. On the right-hand side, that were the sum, the vector sum of the three forces involved. The last one will be external force in addition to the spring elastic force and air resistance. If you just see rearrange this equation, we can obtain a standard second degree inhomogeneous differential equations. Therefore, the rest of the work is just how to solve the differential equation mathematically. So that is a good example of how to apply Newton's mechanics to solve the variety of problems in which force is the key. So every effort should be made to identify and to quantify the force acting on the object. Another aspect of the Newton's mechanics is its integration form. Here in the original Newton's second law, we see the differential form, that is the second derivative represents the acceleration. What would happen if we do integration in space and time? That is very important issues in the Newton's Newtonian mechanics, actually. Actually, that also provides the starting point for other mathematicians, such as Lagrange and Hamilton, to introduce their analytical mechanics. Integration can be done either in space or in time. Let's do the integration in space first. If we multiply dx on both sides and do integration from position 1 to position 2, we can solve this integral by first rewrite the acceleration as a dv dt. And then if we shift this dt under the dx, we can simplify the integral as v dv from position 1 to position 2. Okay. Every student who have started calculus know how to do this integral. When we regard this familiar form, half mv squared, or if you just use the delta sign, represent the change of this quantity. So by integration in space, we can obtain this simple relation. And by introducing two quantities, work and kinetic energy. Okay, notice that this is the first time the idea of energy is invoked. That is integral can be called as the work energy theorem. So the work done by the external force is equal to the change of energy of the system. So that is a very important and basic theorem in Newtonian mechanics. In the special case, of course, if the work done by the external force is 0, then we will obtain the energy conservation law, in which delta E equal to 0. In other words, in the absence of work done by external force, the total energy of the system will become a constant. that is another idea. This is another motive for Lagrange and Hamilton to build their analytical mechanics. We're going to discuss this issue next time. You can argue that this work energy theorem can be considered as the cumulative effect in space of the force. So we're not dealing with the force at a particular state. Instead, we are considering a process in which the work is done. So what would happen? Well, the energy will change. Similarly, we can do the integration in time, starting from Newton's second law. And then if we multiply dt on both sides and do the integration, definite integration from position 1 to position 2, let's focus on right-hand side. If we cancel this dt, this integral became so simple, and we can obtain the result right away. So that is a change delta mv. So mv, if you still remember Newton's mechanics, you know that mv by definition is called momentum. Okay. It's different from kinetic energy because momentum is a vector. The carried out, you must describe not just the quantity, magnitude, but also you have to describe the direction. So I put these two integrals side by side, so you can appreciate that how versatile the Newton's second law is. We can just move from his differential form to the integration form, integral form. Similarly, the simple relation between the impulse, this integral is defined as impulse, and the change in the momentum is called the impulse momentum theorem, similar to the work energy theorem. Again, you could argue that the impulse momentum theorem can be considered as the cumulative effect in time of the force. So from here, you can see that space and time are related, very, very intricately related. The consequences of this integral have different outcome, but they still remain, connected, correlated. So it could be argued that the space has no sense of direction because we generate the scalars, which is a change in energy. Energy doesn't have direction. Energy just the scalars, the quantities of something or metrics of something. However, but time does. It would appear the cumulative effect in time still can be traced, it can be considered as associated with certain time or motion. So that is a difference between these two theorems. In passing, I would like to point out that the Newtonian energy defined in this in his integral form of the second law differs from that introduced by Leibniz, so-called living force. Nowadays, we know that the so-called living force used by Leibniz is a product of mass and the v squared. Actually, Tesla also used this idea, Leibniz idea of energy. Of course, more people, this is just a relevant issue we can discuss further because Leibniz idea about living energy or living force. So be careful, living force has nothing to do with the force defined in Newtonian mechanics. Okay. So we're talking about the living force in relation to the more recent idea about the potential energy and also the energy conservation or energy transformation. That is the essence of Newton's Newtonian mechanics. Okay. In addition, Newton also not only provided the foundation, he laid the foundation for mechanics, but also Newton was the first person to discover that there is a universal gravitational law about the force. It's a force formula. So this particular force is called universal gravitational interactions, and can be described perhaps just by trial and error by this simple formula. So that is a force between the two objects. Again, this is another demonstration that Newton's third law is relevant. So the interaction between the two objects, or a gravitational interaction, involves two forces, a pair of forces. One is a force on object I come from object J. Another is force on object J come from object I. These pair of forces are equal in magnitude, but opposite in their directions. So their formula, the formula is for the amplitude, the formula are the same. So that is a very important discovery. So not only Newton laid the foundation for the mechanics, but also he actually discovered the gravitational force. By using, if this eventually, and Newton has applied his new mechanics to describe quantitatively the Kepler's three laws about the orbit of the planet if sun is considered as the center. So that is a great breakthrough in human history. You could argue that without Newton's Newtonian mechanics, and human would be still in the Plato's cave. Today, even high school students can actually appreciate the Newton's Newtonian mechanics by approximate the orbit of the planet as a circle. In doing so, we can simply combine Newton's second law with his formula for gravitational force. By using very simple algebra, we can predict the velocity of planet, such as the velocity of Earth about the sun. So that is some of the greatest achievement made by Isaac Newton. Of course, if the number of object increase, and you can imagine that in principle, we still can apply Newton's mechanics to describe and predict. However, there's no guarantee we still can get the accurate or analytical formula. In fact, when the number of the object in the system is more than 3, including 3, and one must be obliged to using appropriate approximation method, such as different orders of perturbations. Otherwise, we cannot find any quantitative solutions. So that is a reality. Perhaps that is one reason after Isaac Newton, mathematicians such as Lagrange and Hobbiton had decided to rewrite Newton's basic law into different form, so that we can still, to some extent, without considering the force. Okay, that is our topics in the future. because that is the motive to introduce so-called analytical mechanics. Okay. Of course, as a number, this is something inevitable. For example, if you want to deal with, say, the gas, if you want to describe the ideal gas, then by Newton's Newtonian mechanics, then you have to derive the 3 equations, because it's a 3D motion. You have derived 3 differential equations for each particle or each atom. Okay, so you can multiply the total number of this particle by 3. So you can see the coupled equation is actually these equations are not independent; they are coupled differential equations. You can see that the task, the mathematical challenging, is enormous. Okay, even you can invoke some superconductor computers, computers. I don't think you can solve this problem. Okay, that is why, in my opinion, that Newton's law can primarily applied to study the 2 or 3 very finite number of the object. Okay. Otherwise, we have to follow the analytical mechanics. That would be our next subject. Okay, I hope that this discussion will give you some overall pictures about Newtonian mechanics and why forces are treated as the very important concept in Newtonian mechanics. Okay, of course, gradually we'll notice that, and there is one question Newton didn't answer. That is how fast this action, namely the gravity, can propagate in space. I think that is the only question Newton didn't answer. But in many practical problem solving, who cares? It's not an issue. Okay? It's not an issue. It could be faster, could be very close to the speed of light, as people advocated nowadays in the context of so-called gravitational wave. But is that the only reason? We have to abandon Newton's approach. Instead, we have to adopt Einstein's general relativity. Think about it. Okay, I will stop here and enjoy your viewing, and please make the suggestions as a comment so that I can improve my presentations and also to answer your new questions. Thank you for watching. See you next time. Goodbye.